So we will begin this class. Once again, very good day to everybody. This is wireless networks, and in today's class we discuss about the features of propagation of radio waves. Actually, last class we discussed about wireless communication systems. So how we will propagate through radio waves. So that we will be discussing. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. Right. So in this class, we discuss about the various propagation characteristics of radio waves. Then we identify the spectrum of radio frequency. Okay. We'll understand the wave characteristics. What are the characteristics of the radio waves? For example, very low frequency, low frequency, medium frequency, high frequency, very high frequency, so that we will be characterizing. Okay, so we understand the characteristics of high frequency waves. Okay, how the radio wave propagation actually acts. Okay, then the EM wave, electromagnetic wave in free space, about the transmission path, about the reception path, transmission loss, very important, so that we'll be discussing, and the ground wave propagation or maybe surface wave propagation, so that will be discussing. So this is radio waves normally in the RF, radio frequency spectrum. So we'll be having several frequency ranges. Okay, so each of the frequency ranges will be having different propagation characteristics. So here every part of the spectrum we will be using it in the specific applications. For example, even if you can see like the earth, okay, troposphere, ionosphere, several layers we have. Yes, okay. So the communication satellite will be propagating with the transmitter antenna. Okay, so here we'll be having receiving antenna. So here we'll be having sky wave propagation, space wave propagation, surface wave propagation also. So here the propagation characteristics, especially for the radio waves, is all about the frequency. Okay, so it shows higher dependency on the frequency, which means that the waves acquiring the lowest frequency portion, okay, in the electromagnetic spectrum, you can call it as the radio waves. Okay, right. So here we have very low frequency. Very low frequency means which than with this kilohertz gaja. Okay, 3 to 30 kilohertz. Okay, so maybe for the worldwide telegraphy, common communication, okay, that will be using VLF. And then low frequency, okay, what is done, which use kilohertz gaja. Okay, so the navigation aids, maybe point to point long distance communication, for this you will be using low frequency. And then which use done, which mean kilohertz gaja, but especially for navigation we will be using medium frequency. Okay, and then high frequency, which done with this megahertz gaja. Okay, so you maybe for the communication between 2 points we will be having moderate distance or maybe short wave broadcasting, especially for distance places. So you will be using high frequency. Okay, very high frequency with this done which use megahertz. So especially for long distance communication like radar, telephony, frequency modulation, FM, frequency modulation. Okay, so there we will be using VHF. Okay, UHF, which use then which mean megahertz, especially for TV communication. Okay, radar for short distance communication, you can use this one. For example, I told you when I was in Middle East, Bahrain, Saudi Arabia. Okay, I bought the receiver from Hindustan. Then I went to the flight. I came Bahrain. Okay. Then I asked the TV operator to tune the signals. The same language what I saw in India, I can see in Bahrain. So that communication, UHF, ultra high frequency, that signal I am tuning and I am getting that. Okay. So this is the thing. Okay. Super high frequency, which means then this means megahertz gaja. So that is super high frequency, especially for satellite communication, radar, radio television relay links that you will be using. Okay, then you will be having extremely high frequency, 30,000 to 300,000 megahertz. So that much you can use it in the experiments, especially for if you are a very new beginner, that you will be using for the extra high frequency, EHF. Okay. So there is also another one frequency, extremely low frequency band, ELF. Okay, 30 to 300 hertz. Okay, so and wavelength also 10,000 to 100 kilometers. So that much distance you can experience. Okay, so frequency you can use it for the penetration of the waves for greater depth of the ground. Okay, so that much you can use even for oceans also, long down you can use this kind of communication. Okay, so maybe for submarine you can establish communication with the case of ELF. Okay, so in the frequency band, okay, we'll have VLF, very low frequency, 3 to 30 kilohertz, 20 to 100 kilohertz, VLF plus LF, very low frequency plus low frequency, then low frequency plus medium frequency, 100 to 535 kilohertz, 535 to 1600 kilohertz, medium frequency, medium frequency to high frequency, 1600 kilohertz to 30 megahertz. Okay, so this is the frequency that we'll be experiencing. Okay, and in order to identify and study the wave characteristics, the frequency bands we can divide into several waves. Like we'll have VLF, very low frequency, 3 to 30 kilohertz. So normally you will be using this VLF for ground wave propagation. Okay, so since they are very low frequency, they generally will be having longer wavelength. Okay, so that is the reason you can travel like thousands of kilometers along the surface of the earth. So that is the very low frequency. But you cannot use it for the normal traditional communication because the bandwidth is limited by the low carrier frequency of the waves. Okay, so here waves are propagated by reflecting through the lower portion of the ionosphere and the earth. So by reflection only this wave propagation takes place. Okay, so here it means that the propagation or maybe the wave is in the guided format, okay, within the waveguide. Okay, in the similar way the frequency waves are guided within the region of the ionosphere and the earth. Okay, and here the approximate height which is possessed by the waves lies between 70, okay, Ethamish than Saxon kilometer you will be having distance. Okay, right. But the waves very low frequency, of course it is going to offer low attenuation, okay, at the frequencies around 20 kilohertz, and for longer distance it needs antennas. We will have like antenna of different sizes. Okay, so the attenuation provided is 30 decibel per 1000 kilometer. For every 1000 kilometer it is going to provide an attenuation of 30 decibel. Okay, and the transmission method is inefficient. Okay, but you can eliminate, okay, the use of the wave transmission variations. Okay, generally if you can say in the case of radio waves it is VLF plus LF, very low frequency and then low frequency, and the range would be like 20 to 100 kilohertz. Igrama than use kilohertz. Okay, so frequency also will be using the sky wave propagation. Okay, so up to a distance of 1000 kilometers like ground wave propagation will be used. More than 1000 kilometers you will be using sky wave propagation. Okay, so up to 1000 ground wave, more than 1000 sky wave. Okay, the ground wave propagation generally provides relatively very less attenuation. Okay, so sometimes received signals also will occur some changes. Okay, so normally the propagated signals in this range are not subjected to fading problem. Okay, so signals transmitted in the night hours during the night are much more stronger than during the daytime. Okay, even in the waves that we try to generate. Okay, so in the night it will be much more stronger, day it will be very weak because of the disturbances, interference. Okay, then we have characteristics of radio waves which are a combination of LF and MF, low frequency, medium frequency. So the range would be like 100 to 535 kilohertz. So the frequency range will be for the sky wave propagation when the distance is moderate, very less distance, high. Okay, so with the increase in frequency your attenuation will be increasing. Okay, in the case of ground waves. Okay, so during the day day has, there will be higher absorption in the skywave propagation, especially for higher frequencies, so that will not be suitable for the long distance communication, because the distance, very, very moderate. Okay. So, but definitely there will be, good reliability in communication, especially during the night hours. Okay, right. So with the increase in frequency, the range of the ground wave propagation is actually reduced. So here the characteristics will be ranging from 535 to 1600 kilohertz for LF plus MF. Okay, so you can use it in the radio broadcasting application. Okay, so when this skywave propagation in daytime leads to complete absorption of the signals. Okay, so during day hours broadcasting, we will be using ground wave propagation. Okay, but in ground wave propagation during the daytime, the signal strength will be having rapid reduction, especially in these frequencies. Okay, then we have MF plus complete HF, medium frequency plus high frequency. Okay, so the range is from 1600 kilohertz to 30 megahertz. Okay, so for example, here we will have line of sight, beyond line of sight. Okay, so maybe he is at a line of sight of 4.3 kilometer. He is at a line of sight of 8.6 kilometer. Okay, and he is in a below line of sight 11.2 kilometer. Okay, and this is the TAR. Okay, so that way we are experiencing a difference in the distance. Okay, medium frequency and complete high frequency. Okay, so in the frequency range, it is going to exceed 1600 kilohertz. Okay, so for short distance, the ground wave propagation would be used. Okay, so here for this frequency range, a higher attenuation of the ground wave is actually noticed. So as far as the long distance communication is actually used, for long distance communication, you will be using skywave propagation. Okay, and the maximum usable frequency, okay, is nothing but the upper limit of the communication will be showing dependency on the distance, height, along with the electron density at the point of the reflection of the ionosphere. Okay. So the lower frequency limit depends on the noise level, of course the absorption, okay, internal absorption over the path. Okay, and there is an optimal frequency level, okay, some threshold level, okay, which is considered at around the 15% below the upper limit of as this frequency, the short term fluctuations are considerable. So up to 15%, okay, fluctuation, okay, other than that, greater than 15%, it cannot handle. Okay, right. So for our communication beyond 1000 kilometer, we have to determine the optimal frequency by the F2 layer. Okay, so while the distance is from 200 to 1000 kilometer, so the maximum usable frequency is done by the E layer. Okay, then we'll understand the characteristics of high frequency waves. As I told you, we have the transmitter, this is the atmosphere, so the reflection patterns only we will be having. Okay, so ground wave coverage, skip zone, okay, where the signal is not actually identifiable or maybe detectable. Okay, so here the range would be like 3 to 30 megahertz, and long distance communication is possible with the skywave propagation. Okay, long distance means fakat skywave. Okay, below that, okay, ground wave. Okay, so at these frequencies, the ionosphere absorptions are very, very low. Okay, so even the miles of propagation distance is also achievable. Okay, so that long distance is achievable. Okay, because of the skywave propagation. So when short distance communication is actually required, then low frequencies will be used. Okay, so during low frequencies, here D layer, okay, E layer of D layer. So we have layers. D layer will be introducing appreciable attenuation. So these are the characteristics of waves with a frequency above 30 megahertz. So above 30 megahertz, space wave propagation is practically used. Okay, very rare cases, the frequencies above 30 megahertz will be having like reflections by the ionosphere, and the transmission range is often lesser than the 100 miles. So here there will be some interference, some problem of interference. So that is maybe there will be some buildings, so that it will be reflecting, and that will be creating some disturbance or maybe interference problem. Okay, so at these frequencies, the major applications involve broadcasting of TV signals, radar, aircraft, radio relay systems. Okay, for example, like you have rain, too much of wind, then you see the TV antenna, it changes, then you will not see properly. Okay, so what you have to do, you have to go to the balcony and change something. Okay, only then you will get the signal. So this is what the reflection patterns, okay, especially in the case of TV type of communication. Okay, so for short distance radio communication, we will be having point to point, like mobile walkie-talkie that you will be using. Okay, so maybe you pull this one and you speak like this. Okay, so that walkie-talkie you can use in this type of communication. Okay. Okay, so then we'll have radio wave propagation. So that is actually coming out from skywave propagation. So here from the Earth's surface, we have reflected wave, okay, across the different layers, and this is the penetrated wave. Okay, so from the antenna, it is actually reflecting. Okay, right. So radio wave propagation is all about how you try to deal with radio waves when the waves travel from one end to the other end. So this one you will call it as the wave propagation, or maybe propagation of EM wave, electromagnetic wave. Okay, so radio wave transmission, of course, is a very good prominent method for which you are going to transfer information from one end to another one, and you are going to propagate waves from one end to the other end. Okay, especially for radio communication, in order to transport signals, okay, like in short range or maybe long range, you can use radio wave propagation. So here we'll be having applications in radar, direction finding. Okay, for example, any particular direction you have to find. Okay, remote machine controlling. Okay, so that you can use for radio wave propagation. And high frequency current in the antenna terminal will be having electromagnetic energy. So that is in the form of the waves. Okay, so here we will be having similar properties of light. So that is the velocity of light. So similarly, the radio waves also will find some properties similar to the velocity of light. Okay, so radio waves in space will be oscillating in free space with the velocity of light, 3 multiplied by 10 power 8 meter per second. Okay, so we'll be having, electromagnetic waves where we will be having both electric component as well as magnetic field component. Okay, here the radio waves will be traversed in nature, which means that the components oscillate perpendicular to the direction of the motion. Okay, so this is the electromagnetic waves in the free space, E, H, E. So that E will be going, H will be going, sine, cosine. Okay, so you can go for like anything, X, Y, Z, or maybe X, Y, Z, anything you can take. Okay, so this is for the free space. Okay, so here it should be noted that the initial polarization, which is actually provided or maybe produced by the antenna, depends on the orientation with respect to the ground. Okay, so the antenna placed in the horizontal as well as vertical will be producing both horizontal as well as vertically polarized waves. Okay, so these are, we identify the waves traveling between the transmitter and the receiver. Okay, so all the waves will be maintaining the actually produced polarization during its propagation. So we will be having reflection, refraction, okay, and diffraction. Okay, so that is how you try to reflect the waves. So radio wave propagation, generally you will be having the phenomena, okay, where the wave travels between the transmitter and the receiver. So the ways in which the waves will travel between transmitter and receiver is by propagating in free space or maybe through the guided medium. Okay, so the guided medium will be like waveguide or maybe like a coaxial cable. Okay, so that we will be using. Okay, so when the wave is propagating through free space, then during propagation, the available spectrum must be shared across each of the users in a proper scheduled manner. Okay, so this is the reception part. Here we'll be providing services to the devices which are in close geographical conditions. Okay, so if there are close geographical conditions, for example, here we have like too many buildings nearby, there will be interference problem. So maybe if you are talking among others, okay, there will be some interference problem. You talking to him, I talking to you, she talking to you. So that interference will be there because everybody are in close geographical locations. Okay, so in this case, when propagation takes place through the guided media, which means that the signal will be having very less attenuation with the other users. Okay, but definitely the users also will get to use the full range of the frequency band. Okay, so here when the wave propagates through the earth environment, then the manner of the wave propagation does not depend on the property of the waves, but it depends on the environmental condition. Today, Isik, signal Yakshi, Savok, signal Yamun. So that is the way it depends, not depend on the properties of the waves, but on the environmental conditions. Okay. So the effect of the medium in which the wave propagate is generally of great importance because it is going to account for the intermediary objects in the path. Okay. So this is the practical radio wave propagation. So the environment through which the radio waves propagate will be having several discontinuities like maybe hurdles or maybe variations in the medium parameters. So for practical conditions, maybe the earth and the objects which are present in the surroundings are very important. Okay, and here the behavior of the wireless channel, okay, must be properly understood if you have to design the effective radio wave communication system. So that is actually irrespective of the distance of the transmission. Okay, so for this one we will be using Maxwell's equation. We now move into transmission loss. Okay, so we are going to identify or maybe examine what nature this electric field and magnetic field will actually exhibit, okay, within this conducting and insulating waveguide. Okay, so when the transmitting antenna is going to radiate a signal, generally it will be spread for a quiet region. So when the transmitting antenna is going to radiate a signal, generally it will be spread for a quiet region. So this is what we saw. Okay, right. So that at the receiving antenna, the receiving power, okay, is of comparatively small fraction than it is actually radiating one. Okay, so here if you can see, this is actually the baseline. Okay, so we get like reflection patterns like 0 kilohertz, 25 kilohertz, ELIC, use, EQ, so different ways that we try to generate. Okay, so here we will be having some transmission loss, okay, of the order of 10 power 15 to 10 power 20. Okay, so that is actually existing between the two antennas. Okay, so apart from this loss, you can conclude whether the signal which is received, definitely we are trying to utilize it or maybe not. So that is how you try to make the maximum usage of the transmission loss. Okay. So we have like different modes of propagation: ground wave propagation, sky wave propagation, space wave propagation, tropospheric scatter propagation. We have different modes. Okay, so these are all forms of the radio propagation. Okay, so this classification is associated something with the operating frequency, the range between the two antennas, the distance between the two antennas, how you try to reflect, how you try to refract, how you try to diffract. This all depends on. Okay, right. So here we have surface wave propagation. Okay, from the transmitting antenna to the receiving antenna, we have the propagating wave. Okay, so here we will be having surface wave propagation. Here the radio waves transmit by passing through the semiconductor surface of the earth. Okay, so here the transmission will be occurring at a region close to the surface of the earth, at the surface close. Okay, right. So that is beyond the horizon. So the mode of propagation requires vertically polarized waves, because the horizontally polarized waves will be absorbed by the earth. There will be only vertically polarized waves. So because of this, we will be having the surface wave propagation. Okay. So here the propagating waves will be following the earth's curvature. Okay, so generally for VLF and LF it will be very suitable, very low frequency and low frequency. And here the frequency range will be 30 kilohertz to 3 megahertz. Transmission distance will be 100 to 1000 kilometers. So that much only. Okay, so beyond 3 megahertz, see, we have the upper limit to be 3 megahertz. Beyond 3 megahertz and beyond 1000 kilometer, the attenuation generally begins. The attenuation of the transmitted signal by the earth will begin. Okay. So this is the independent work 2 for you. Okay, types of analog modulation, the features, types of digital modulation, DM, their characteristics.